So today we are going to continue looking at the periodic table. Our texts say that we need to identify that protons determine an element's identity and valence electrons determine chemical properties, including reactivity. And we're going to interpret the arrangement of the periodic table, including groups and periods, to explain how properties are used to classify elements. So some things you need to understand by the time we're done is that the periodic table is arranged by atomic number and shows a tendency for properties to repeat in a periodic pattern. And it can be used to predict the properties of an element. So we're going to kind of look at what are some patterns or trends found in the periodic table of elements. How are elements on the periodic table organized? How is chemical reactivity of an element determined? And then how does the arrangement of elements on the periodic table allow for the prediction of undiscovered elements and their properties? Because there are a lot of new elements. They're found pretty often and they fall right into the pattern that is already set on the table. So how are groups of elements similar and different? And how are periods of elements similar or different? So a group on the periodic table is a vertical column. So the vertical columns on the periodic table are called groups. Sometimes they're called families because they have similar physical and chemical properties such as reactivity. And reactivity just means how easily it bonds with another element. So here the highlighted family is the alkali metals. Now hydrogen is over there and it's in that column because it has one proton and it's the first element, but it is not actually an alkali metal. It has some similarities to them, but it's not a metal. It's the only metal on that side of the table. So hydrogen is over there, but it's not one of the alkali metals. You can tell how many valence electrons an atom has by the group it belongs to. So valence electrons are the outermost electrons. If it's in group 1, it has one valence electron. And we'll talk about that a little bit more tomorrow as we mark our periodic tables up. So watch this real quick about the alkali metals.
Whether you've left school or you're still at school, you can appreciate the sheer fun, mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present. These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson:
Never mixed alkali metals with water.
Periods on the periodic table are the horizontal rows. There are 7 periods on the periodic table. Now they have dissimilar physical and chemical properties, so they don't have any much to do with each other like the families do. But the thing they do have in common is the number of energy levels in each atom. So all elements in period 1, which are only hydrogen and helium, they only have 1 energy level or orbital. If they're in period 2, they have 2 energy levels. If they're in period 3, they have 3 energy levels, so on and so forth. So the one that's highlighted here is period 4. So every element in that row has 4 energy levels. Another thing we would look at, another pattern on the periodic table that we need to know about are the metals, metalloids, and nonmetals. So we have this thing called the staircase, and the staircase is where you see the blue elements on this periodic table. We call that the staircase. On your periodic table, it should be a bold line there. Well, everything to the left of that, except for hydrogen, is a metal. So you see that the majority of the elements on the periodic table are metals. Everything to the right of that is a non-metal. And then you have the blue ones that are your metalloids. They have characteristics of both metals and non-metals.
Dear Tim and Moby, what is metal and why do we need it? Thank you, Side Note 3540. You use things made with metal every day. Cars, jewelry, silverware, shoes, belts, dishwashers, school bells, light bulbs, pens, cell phones, and mailboxes, just to name a few. Oh, yeah, robots are made of metal too. But just what a metal is kind of hard to define. A chemist might tell you that metals are elements with metallic qualities. Well, that's not as silly as it sounds. See, on the periodic table, every element falls into one of 3 categories: metals, nonmetals, and metalloids. Metals are the most common type, and they're defined by certain physical and chemical properties. In terms of their physical properties, metals have luster or shininess, are good conductors of heat and electricity, are solid at room temperature, except for mercury, are malleable, or able to be hammered or bent into shape, are ductile, so that they can be stretched into wires or other shapes without breaking, have hardness or resistance to scraping and abrasion, and have elasticity, the ability to go back to their original shape. Well, most metals have most of these qualities. Well, hey, I'm doing my best. We can narrow down what metals are by looking at their chemical properties. First, they have positive valences, which means that they give electrons to the atoms they bond with. Because metals give up negative electrons so easily, they tend to form cations, positively charged atoms. Also, metals oxidize, corroding when they're exposed to dampness. No, you can't usually just go outside and pick metal up off the ground. Only native metals like copper, gold, platinum, and silver are found by themselves, and even then they're usually buried in the ground. Most metals are found in veins mixed together with ores, masses of mineral that carry a lot of metal. The veins are mined for the ore. Removing impurities from the ore so that only the metal remains is called refining. Well, after metal is refined, it's often mixed with nonmetals or other metals to form alloys. Alloys have properties that make them more useful than pure metals. Bronze, an alloy of copper and tin, is harder and more resistant to corrosion than either copper or tin by themselves. Steel is an alloy of iron and other elements, especially carbon. Since carbon adds hardness, steel has a lot of industrial uses, including cutting tools, welding, and car and airplane parts, and armor. Eating utensils are often made of stainless steel, which is strong and rust-proof. Yeah, I don't know what this one's made of.
Some key characteristics of metals you need to know is that they usually are silver gray in color. They're usually solids at room temperature. There are a couple of exceptions like mercury, and gallium. They are lustrous. They are malleable, meaning they can be bent, shaped, or hammered into flat sheets, or like you can make coins out of them, metal coins. They're ductile, which means they can be made into wires. They're sonorous, meaning they make a metallic sound when struck. They have high melting and boiling points. They're usually good conductors of heat and electricity. They are usually high density, and many of them are magnetic. Characteristics of nonmetals you need to know is that usually they can exist as solids, liquids, or gases at room temperature. So it's a variation there. Many of them are dull. They're not shiny. They have no luster. They're brittle, meaning they break easily. So they're non-malleable, non-ductile. They bend very easily as solids. Many of them have low melting and boiling points. They're poor conductors of heat and electricity, or non-conductors. They have very low density. Remember, density means how much matter is concentrated into an area. So they have pretty low density. And most of them are not magnetic. Actually, I don't think any of them are magnetic. Then finally, we have our metalloids. There are not a lot of metalloids, and metalloids are very useful. Inside your phone, you'll find lots of metalloids. Silicone, germanium are two that are used quite often. Usually they are solids at room temperature. They might be shiny, they might be dull, they could be malleable or not. You may be able to make wires out of them, so they may be ductile. Some of them are brittle. They're semiconductors, meaning they let some electricity through or heat pass through, but not as much as a regular metal. Their boiling, melting points vary. They have varying densities. Because of this kind of blending of the characteristics, that's why a lot of these are used in electronic devices, because your phones, you don't want it to get too hot, so you use a semiconductor. So they still get hot, like my phone gets hot. But you don't have the same effect as you would have used a piece of iron. So there's still, this is kind of an overview. We went over generally what you find on the periodic table before. Now we looked at kind of what the patterns are. Tomorrow we'll really look at breaking down the periodic table, and you're going to be marking one up with a lot of information that you'll need. That periodic table will be your best friend until we finish out this unit. So that's it. Have a good day.